I'm going to share the screen. All right, and here we go. So 4.3, we've got logarithmic functions, all right? So we're gonna start off like we've been doing with what we know, and then, oh, I forgot to type it in, but what's new? So what we know, we talked about on Monday that there's something called an IRA. It's an individual retirement account. And we said that on average, and we're talking like not like over 3 years, but like over like 30 years, okay? So over the lifetime of your IRA, the average rate of return is you get about 6% interest per year, okay? And so we said that like right now, the most that you can put into an IRA each year is $6,000. So you can't like take a whole bunch of money, put it in there and just like let it grow for the individual retirement account. The government does put a cap on how much you can put in. And so that's where this $6,000 number comes from. And on Monday, we learned how to write a function that models the value of an IRA. And we knew from the 6% that we were going to immediately be thinking f of x equals ab to the x. And we knew that our a value was our initial deposit, so $6,000. And we knew to find the b that we do not want to put 6 in for b, okay? But instead, we had to use that formula 100, right? That's like our initial amount plus 6% because we want to make sure this money is growing. And then we divide it by 100 to turn it into a percent. And that was raised to the power of x. And then we wanted to clean that up a little bit so we could use the equation more easily. So we got 6,000 equals 1.06 to the power of x. And then we answered questions like, how much is your money going to be worth in 30 years? And we realized that in 30 years, we would earn almost $30,000 off of this just by putting in the $6,000 and doing nothing with it. So let's kind of backtrack a little bit because I think 30 years from now sometimes feels like a really long time, right? Who knows where you're going to be in life at that point? I hope it's happy. I hope it's healthy, but we don't really know where we're going to be in 30 years. So let's maybe think a little bit more short term. What's going to happen in 5 years? Okay. So if I want to find out the value of my investment after 5 years, all I need to do is take the 5 and plug it in for the x. So we get f of 5 equals 6,000 times 1.06 to the 5th power. And remember, we're thinking like we want to be a little bit more grown up in our math and our calculations. So we're not going to like type in one part and then another part into a calculator, but rather we're going to try and type the whole thing in at one time. And then because we're looking at money, we wanted to round to 2 decimal points because more than 2 doesn't really make sense when we're looking at dollars and cents, right? And so when we type this in, we should get $, 8029 and about 35 cents. Okay. So I know that we said on Monday that, wow, you could put in $6,000, forget about it, and earn $30,000 in 30 years. That's pretty cool. But even if you're like, I just want to put it away for 5 years and see what happens, you made over $2,000 without having to do anything other than put in your initial amount, okay? And remember, we said you don't have to put in all $6,000. You can put in as much as you want, but you can't put in more than that. It's kind of similar to like office hours or Val's tutoring sessions, right? You can pop in for like 10, 15 minutes. That's totally fine. You can stay the whole time if you want. That's also fine, right? So there's a little bit of flexibility with the amount of money that you put into your IRA. All right, so this next section, which let's title What's New, okay, is thinking about the value of our investment and not finding the value, but actually figuring out how long it's going to take for something to happen. So some of us might have life goals like, I want to buy a car at some point in my life, or I want to buy a house. I don't want to pay rent forever. I want to buy my own house, or I want to, I want to get a dog, or I want to have kids and I want to save for their college education, or whatever it might be. You might have some financial goals in your life. And so being able to determine when your investments are going to double or triple is pretty handy, because you can figure out when are you going to get the amount of money that you want to have so that you can do with that money what you want to do with it. So let's take a look at this. When will your investment double in value? So we know that we have our f of x equals 6,000 times 1.06 to the x. Now 6,000 is the initial investment. So when it doubles in value, how much are you looking to have in your account? $12,000, exactly, right? We want $12,000 more, or not more, but that's what we want as a balance. So instead of f of x, we can replace that with 12,000. And we know that that's going to equal our function that tells us like how much we're going to have, right? So the question here now is, how do we get the x out of the exponent? Okay. So here's what we're going to do. Our first step in solving these exponential equations is going to be to isolate, not the pencil, the highlighter. We want to get 1.06 to the x by itself, okay? So how do I get that b to the x by itself? What do I need to do? Divide by 6,000. Excellent. So let's do that. We're going to divide the black pencil. All right, we're going to divide this by 6,000. We're going to divide the other side by 6,000. All right, we know 6,000 and 6,000, those reduce to 1. And then 12,000 divided by 6,000 gives us 2. So what that gives us as a new equation is 2 equals 1.06 to the x, okay? So we have isolated our b to the x. Now, you could guess and check. You can plug numbers in for x, which is fine. But what I'm really looking for, so when you see a question like this on an exam, what I'm looking for is for us to be like, oh, we need an algebraic way to get the x out of the exponent. And so the way we're going to do that is at this point, all right, we're going to use logarithm to get the variable out of the exponent, okay? We're going to use logarithms to get the variable out of the exponent. And here's what that's going to look like. I'm going to show you what it looks like now, but we're going to talk about it a little bit more deeply in the lesson, okay? So the way we're going to do it is we're going to write x, or the exponent, equals log, so L-O-G. We have to write a base for the log. Now, in this bracket right here, what is the b value, or the base? 1.06. So guess what our base is when we write it in logs? 1.06. Okay, so this base right here is going to be the same as the base for our log right down there. So 1.06. The number on the other side, the 2, that's going to be the number that we are logging. Okay. So x equals log base 1.06 of 2. Now, some calculators can handle this right now, but a lot of other calculators, you need to change the base so that you can type it into your calculator. And so what the change of base formula looks like is log of 2 divided by log of 1.06. Okay. Now I'll give you a moment if you have a calculator to find the log button on your calculator. Now, as soon as you type log in your calculator, what happens is it opens up a parentheses. You didn't do that. The log button opens up a parentheses. The catch is, because it opens up a parentheses, you have to remember to close that parentheses before you type in the next step, which is the division. Does that make sense? So when you type in log, it will open a parentheses for you. Make sure you close it, even though you're not the one who put it there. If you do not close the parentheses, you're going to have all this correct work, and then you're going to type it into the calculator and get the wrong answer. And that's so sad, okay? So if you're using a calculator, it opens the parentheses, you have to close it, okay? So I'll give you folks a moment to type that into the calculator. And I'd like us to round to 3 decimal places for our answer. So after you've typed it in, if you could type in your rounded to 3 decimals, that would be wonderful. Yeah, I'm getting about that too. 11.896. And the units for this, folks, dollars? What are we labeling this with? Years, exactly. So if you invest $6,000 in about 11, almost 12 years, you will have doubled your money, okay? Now, the cool thing about exponentials, though, is that the longer you let that sit, the amount of money in there, the faster it's going to grow. Because if we think about our exponential curve, it kind of starts like this, and then it really picks up steam. So when you're thinking about your investments, the longer you can invest something, the closer you'll get to it getting bigger faster. And so that means that you're earning more money more quickly, all right? By the way, I am not a financial advisor. I'm just saying this stuff as like sort of general financial knowledge, but you know, definitely take some time to educate yourself on other things financial if you are interested in that. Okay, so let's take a look at something similar. When will our investment triple in value? Okay, so if you were at the STEM core orientation, you know that the keynote speaker talked about this idea of variations in problems, right? What changes, what stays the same? So in looking at the 2 questions, one question says, when will it double in value? The other one says, when will it triple in value? So what's going to change about my setup and what will stay the same? So if we start here, okay, with our original equation, what changes when I'm starting to look for when the investment is going to triple in value? Excellent. All right. So Richard says f of x changes, everything else stays the same. Antonio's very specific. He says the 6,000 is going to become 18,000. Now, do you mean change this to 18,000? Is that what you mean, Antonio? Ah, okay, good. So I love that clarification there. We're going to change, maybe we say the f of x, right? The f of x changes to 18,000 because we want to know when it's going to be 3 times as much, all right? So great job with that, folks. All right. So how does that change the way we solve this? Can we still divide by the 6,000 first? Yeah, we'll divide by that 6,000, right? So let's get rid of this 6,000 and we'll divide that here too. These two will reduce to 1, but this side now reduces to 3. Okay. So instead of 2 equals 1.06 to the x, we've got 3 equals 1.06 to the x. So same kind of problem, different numbers, right? That's what he was talking about. What changes? Just the number. But what stays the same? The process stays the same, okay? So at this point, we're going to use logarithms to get the variable out of the exponent. So how can we write x like we did over here? All right, before that step though, good. Okay, so log base 1.06 of 3. Beautiful. So log base 1.06 of 3, okay? I want us to write this step on a test. I know that you might know exactly how to skip a few steps, but it's really important for me, especially when we're in the remote learning situation, that you show me as much of your thinking as possible, because that gives me the chance to give you as many points as possible, or to see really like where you went wrong, okay? So when we're writing those, please make sure to include this step, and then we can write it as log 3 divided by log 1.06. And don't forget your calculator opens up that parentheses. And so even though you didn't do it, you have to close it. And we should be getting that our money is going to triple in about 18.854 years. Okay. So that's kind of cool because in less than 20 years, you're going to have 3 times as much money in there. And that's just if you did a deposit one time. You didn't keep depositing every single year. Okay. So if you deposit every single year, you're going to triple your money much faster than with this model. Okay. So let me zoom out for a moment. This is our what we know, and then the bottom half is what's new. So the what's new part is we need this thing called a logarithm to help us get variables out of the exponent. That is its job, okay? The job of a logarithm is to get the variable out of the exponent so that we can figure out what it is, okay? All right. So let's go back to some graphing because I think it's important for us to think about what the pictures look like. And then we'll talk about like how to do the various calculations with them. All right, so kind of a what's what we know, what's new here. But what we know is our exponential functions, right? We've seen this f of x so much already. So I'm going to walk through it kind of quickly. We have our x, and we pick values like -2, -1, 0, 1, and 2. And then our f of x, I had left 2 lines just so we could practice what it means to have a negative exponent, right? So if we just plug in the numbers, we've got 2 to the -2, 2 to the -1, 0, 2, not 0, 2 to the 0, 2 to the 1, 2 to the 2. And then we could simplify to 1/4, 1/2, 1, 2, and 4. And then we plotted those points, right? Oops, we plotted those points and we got 0, 1, 1, 2, 2, 4, -1, 1/2, and -2, 1/4. Right? And so we've got our exponential curve. We know it's an exponential growth. We know that there is a horizontal asymptote. We know that this point, our center point is 0, 1, and we know that this horizontal asymptote is y equals 0. Right? Those are all things that we know. Now, when we think about the logarithmic function, okay, the reason why exponentials and logs are in the same unit is because they are something called inverse functions. Okay. And I feel like the word inverse function kind of sounds like fancy sometimes, but let's dial back to like elementary school for a moment. If you had a number and I asked you to add 5, and then I asked you to subtract 5, what would you end up with? The original number, exactly, right? So if I asked you to add 5 and then subtract 5, you would get your original number, the OG number. I like it. So what's kind of neat about addition and subtraction is they are inverse functions. They undo each other. So addition and subtraction undo each other. Let's actually not use that symbol. So plus and minus, they undo each other. What's another pair of operations that undo each other? Multiplication and division. I love it. So multiplication and division, those undo each other. What else undoes each? What other pairs of operations undo each other? Let's see if we can get a little fancier, more like middle school math or high school math. Yeah, square and a square root. I love it. So like if I square something and I square root something, exactly, okay? Yeah, positives and negatives, that goes back to that like plus and minus. They undo each other. And so we actually know a lot of inverse functions, but sometimes we just forget that something we know could be associated with like a fancier name, right? So exponentials and logs are inverse functions. And what that means is that when we have a general exponential function, okay, so let's say we had y equals b to the x. One of the easiest ways to find the inverse function is that you switch your x and y. So what that might look like is not y equals b to the x, but x equals b to the y. And when we switch our x's and y's, then we want to solve for the new y, meaning we want to get the y by itself, okay? And so if we use what we were looking at earlier, if I ask you to rewrite this with logs, you would end up with something like this. Log base, what's the base for the log going to be? Yeah, it's going to be 2, or in our case, a b. So let's write a b for right now. What's the number that's going to get logged? X, good, good, good. So log base b of x equals y. That's where our log function comes from, okay? We use the definition of an inverse where we switch the x and y and we solve for the new y, okay? Now, let's take a look at that same definition, but with the numbers, okay? So some of us already did that, but we could write f of x equals 2 to the x as g of x equals log base 2 of x, right? If we use the numbers from our f of x. So log base 2 of x is what we're going to try and graph right now, okay? Now, if I take x's and y's and switch them to find the inverse, then a really cool way I can do that with the graph is I can take my coordinates and I can switch them and graph them. So let's do our starting point first, 0, 1. If I switch the x and y's, I get 1, 0. So that's actually a point on my log graph. So 0, 1 became 1, 0. Okay. That means that for the x value of 1, I actually have a y value of 0. Okay. So what that means is that log base 2 of 1 is the same as 0. Okay. Log base 2 of 1 equals 0. Someone give me another point from my f of x so that I can switch it, the x and y's, and get a new point on my g of x. That's a nice point from our f of x. 1, 2. Yeah, so this point was 1, 2. So if I switch the x's and y's, I don't get negative 2, 1. I just get a 2, 1. Okay, so 2, 1 is going to be a point on my inverse graph. Okay. That means that an x value of 2 is going to give me a y value of 1. And if we think about what that looks like, it's going to be log base 2 of 2. Okay. Now, if I keep using this pattern, I switch all my x's and y's, let's see what we get. So 2, 4 is going to become 4, 2. And that's going to be this point, which also means that log base 2 of 4 equals 2. All right, let's switch the last 2 points. I've got 1/2 and -1, or log base 2 of 1/2 equals -1. And I've got 1/4 and -2, which means log base 2 of 1/4 equals -2. All right, let's plot those points. I've got 1/2 and it'll be at -1. I've got 1/4 and it's going to be at -2. And if I connect those 5 points, I end up with a graph that looks like this. Okay. Now my exponential function had a horizontal asymptote, but the logarithmic function has vertical asymptote. So vertical asymptote, and our equation here is not going to be x, or not going to be y equals, but it's going to be x equals 0. Okay. All right, any questions on these two graphs here so far? Do you have a specific question about the vertical asymptote? Like, why is it x equals 0? Every single point on this line, it all has the same x value. They're all x equals 0. So together, they make the line x equals 0. Okay, cool. All right, so we've got log functions, we've got exponential functions. Their graphs kind of look similar, and if you forget, if you know one, you can find the other one just by switching your x, y values, okay? But I want to talk a little bit about what happens, like what kind of numbers you can put in and what kind of numbers you can get out, all right? So let me put the graph on the screen with those questions. So for the exponential function, can we put in negative numbers? Like, can x be a negative number for the exponential function? Yes, okay. So for the negative numbers, yes, we can put those in, okay? Can we put 0 into the exponential function? Yes. And can we put positive numbers into exponential functions? And that one is a yes, okay? So because you can put all types of numbers into an exponential function, that's why our domain was from negative infinity to positive infinity, because there was no limitation to the kinds of numbers that you could put in, all right? Now, let's look at negative, positive, and 0 for the output, though. Did we get any negative numbers out of the exponential function? Meaning, were there any points that were below the x-axis? No, right? There's nothing below there. So this is a no. Can we get 0 out? And that answer should also be no. But can we get positive numbers out? And that answer is yes. That's why our range goes from 0 to infinity. Yeah, exactly. Okay, I love the talk going on in the chat. So when we think about the logs now, Okay, this is where we need to be clear on the rules, because I think sometimes when we're in high school, we learn like the short version of the rule and then we don't get a chance to think about, but when could it be? Okay, so can we put negative numbers into a log? Meaning, are there any x values on this side? Like, is there a picture of a graph on that side? No. Okay, there's no picture on that side, so we cannot put negative numbers in. That vertical asymptote sort of is a barrier from where our graph is and the numbers we cannot put in. Okay, can we put in a 0? Like, does our graph ever touch 0? Does it? Yeah, it does not have, you cannot put x in as 0. But can you put in positive numbers? And the answer is yes. So how can we write our domain for logs? Yeah, exactly, Richard. We're going from 0 to positive infinity. And we know that because we asked ourselves these questions, okay? Now let's think about what we can get out of it. Can negative numbers come out of this? Yes, they can. So can a 0, and so can positive numbers. So since all kinds of numbers can come out of this function, we know that our range is from negative infinity to positive infinity. Okay. Now this is something common you'll see with inverse functions, where the domain of the one function is the same as the range of the inverse function, and that the range of one function is the domain of its inverse function. Okay, it's not true all of the time, but it is a good starting point to think about domain and range. Okay, so this next part, I would highly, highly encourage that you put this on that reference sheet that you are going to create for next week's exam. Converting between exponential and log form. So when we have the exponential form, we're looking at y equals b to the x, all right? So we're looking at the parent function. This is the exponential form, okay? The log form, which we kind of talked about, is going to be x equals, because we're solving for the x, log base b of y. So the base in the exponent is the base in the log form. And the y value for the exponential form is the number being logged in the log form. All right. And our exponent here is the same as sort of the y value in the log form. Okay, so being able to go back and forth between these two forms is super, super, super important. All right, well, let's practice using these and also doing some mental math, okay? So example number 1 here, it has log base 2 of 32. That equals x. So right now it's in log form. If we rewrite it in exponential form, what does that give us? All right, so let's maybe color code this the same way we did. We've got our x over here, we've got our base over here, and we have the y value here. And so when we rewrite them, it's going to be exactly like Laura said. It'll be 32 equals 2 to the x. Okay? That's it. Here's your log form. Here's your exponential form, rewriting it. But now we want to solve for x, okay? So now I need to think, all right, 2 to what power is going to give me 32? And that turns out that 2 to the 5th power equals 32. So that means that x equals 5. Okay. All right, let's try a different one. I've got my x equals log base 4 of 64. If I rewrite that in exponential form, I get 64 equals 4 to the x. So that's what that question is asking you. When someone says, solve this question without a calculator, they know that you know how to find exponents. They just want to know, do you also understand that logs are asking you for the exponent in a fancier way? Okay? So 4 to what power is the same as 64? Four to the third. Yep, 4 to the third equals 64, so x equals 3. Okay? All right. I'd like you to take a couple moments and just work through examples 3 through 6. Okay, so I'll give you about 3 or 4 minutes to rewrite them in exponential form and solve for x. And again, these are ones that you should feel comfortable doing without a calculator. Okay, so take a few moments, work through those, we'll check our answers, and then we will move on to some more special applications. All right, I'm going to start to put up some of these answers so you can kind of check as you're working through your own. Okay, so hopefully we all got x equals 2 for number 3. Okay, I think that one was very similar to example 1 and example 2. But somebody help me out here with example 4. So I rewrote it in exponential form. I got 1 over 125 equals 5 to the x. So 5 to what power is the same as 1 over 125? -3. Good, good. Okay, so we want to make sure it's a -3 here. And so that means our x is a -3. Okay? All right, so we try the same thing with the last two. We get 1/16 equals 2 to the x. I know that 2 to the -4 power gives me 1/16. And so that means that x equals negative. And the last one I think is pretty straightforward. We get 9 equals 3 to the x. We know that 3 squared is the same as 9. And so we get x equals 2 for our last one. Okay? So these kinds of questions are really important to be able to answer, not because it's like, oh, look at me, I don't need a calculator, but it makes your process of simplifying questions a lot easier. And most importantly, it shows that you understand what a logarithm is. Okay? All right. So there's a couple questions like that on the quiz for quiz 2. All right. But we're going to finish up here with a couple examples on something called a common logarithm, and then a couple examples on something called a natural logarithm. Okay. So let's do those. I'd like to make sure we finish that up before our 12:30 or 12:40 mark. Okay. So common logarithm. So a common logarithm is a logarithm that has a special base. Specifically, it has a base 10. But since 10 is so common in our math, we call this a common log, and we don't even bother writing the 10. So when somebody doesn't write a number, they're saying that number's 10, and I want you to know that number's a 10. Okay? So a common logarithm is a log with a base 10. So let's take a look at a couple uses of it. Most frequently, we use common logarithms to describe earthquakes and how strong they are, okay? So let's take a look at example 7. The amount of energy released from one earthquake was 500 times greater than the amount of energy released from another. The equation 10 to the x equals 500 represents this situation, where x is the magnitude, difference in magnitudes on the Richter scale. So since we all live in California right now, I feel like earthquakes are more familiar for our brains than maybe people who don't live in California. But when they describe earthquakes, they're like, "Ooh, this was a 3.2 or like a 5.4," and the numbers don't seem that different. But actually, the strength of those earthquakes is really, really different from each other. Okay, so let's find out how different it is on the measurement. So if I have 10 to the x equals 500, how do I rewrite that in log form? X equals log what? Yeah, we could write it as log base 10 of 500, or we could be real fancy and be like, we just learned about this common log. I don't need to write the 10, so I'm just going to write it as log 500. Okay, so those two are the same thing. The nice thing about not having to type in the base, you can just type this right into your calculator, log 500. Because the calculator, when you type log, it assumes you're doing log base 10. Okay, so let's type in log 500 and tell them to 3 decimal places. We should get 2.699. Okay, that answers what is x. X is 2.699. But the other question, what is the difference in magnitudes? What I mean by that is, let's say you have earthquake 1 and it's a 2.0 earthquake. How much, or what would the Richter scale measure be for an earthquake that is 500 times greater in strength? Well, if this is the difference, I need to add that to my original. I get not 2.0, but 4.699. Okay? So what that means is if you have a 2.0 earthquake and a 4.699 earthquake, the 4.699 one isn't just like 2 times bigger, it's like 500 times bigger than the 2.0 earthquake. Does that make sense? Okay. So let's try the second example, right? So this time we have an earthquake that's not 500 times greater, but 8,500 times greater, like 8,500 times stronger, okay, than one earthquake. So the equation that we get is 10 to the x equals 8,500. So if we want to find the difference in magnitudes, we need to convert it to log form. We want to be fancy and say, hey, that's really the same as log 8,500. We know that. We want to type that into our calculator and know we don't need to do a change of base because it's already in the base that our calculator works in. And when we do that, we should get 3.929. Okay? So that gives us our difference in magnitudes. So let's say you had a 2.0 earthquake versus a 5.929 earthquake. It's not just a difference of 3. It's not like, oh, it's 3 times stronger. It's this many times stronger. Like that's how these scales work when we're talking about earthquakes. So when someone says like, oh, we had a 2.0 over here, and someone else is like, we had an 8.0, basically the 8.0 was like a bazillion times stronger than the 2.0. Okay? All right. So let's finish off today. I know it's been a long day, but let's finish off today with some applications of a natural logarithm. Okay. Now, this one is probably something you've also seen before if you've taken a look at exponentials. This is what we typically use when it comes to money. Okay, so the equations that we showed you earlier, those are like, this is kind of an idea of how you could do it, but using natural logarithms is more of like the level up, grown up kind of way of looking at a lot of the scenarios we looked at earlier. Okay, so a natural logarithm is a logarithm with a base e. So instead of writing log base e of x, we write it as ln x. Okay, so that's an L, not an I. ln x. Okay, so whenever we see ln or you see the ln button on your calculator, that is a log with base e. All right. So what is e? All right, e is like, I don't know, kind of looks like a variable, but it's not. Okay. E is a irrational number, meaning it's kind of like pi where it keeps going forever and ever, and there's not quite a real pattern to it. So it makes it hard for us to like write out every single digit, okay? I wanted to show you this part because you'll see this again in Calc 2, right? Or we'll call that Math 151. We don't really need to know about it right now. I just want you to know that E is a number and it comes from somewhere, but you'll learn about where it comes from in a later math course, okay? Now, just like we know pi equals 3.14159, we can say that E is 2.718282. I think like 2.718 is probably enough. But this constant was named by this guy, and you do not pronounce that Euler, you pronounce it Euler, so it kind of sounds like Euler, like gas and oil, not Euler, okay? So Euler is the one who named this constant and found out like, oh, we could use it for all of these things, all right? So what do we use E for, okay? E is used for situations where we're thinking about continuous growth or decay. Meaning, if you see the word continuous in a word problem, you're going to use this equation if it's just like a general population, or if we're talking about money, you've probably seen this A equals PE to the RT somewhere. And again, the word continuous is the clue that you're going to use these equations and not the ones we used before, okay? So let's take a look at two examples where we're going to use A equals PE to the RT instead, all right? So the average rate of return, here's our IRA again. We can take a look at this using a continuous model, okay? Because the truth is when we're looking at any sort of investment, it's a continuous model, not like, oh, every month then they count your interest, okay? So by definition, IRAs are continuous. And so we really want to use A equals PE to the RT to write the equation, okay? All right, so our P stands for the principal amount, but it's the same as your initial value, okay? Just a fancy financial term. P stands for principal, but it's the same as your initial investment. So we can put a 6,000 here. The E is a constant, so we're going to keep it as an E. The R comes from our percent, but we have to change that percent to a decimal. So it's going to be 0.06. And then our T is our time, and we don't know what that is yet, so we want to leave that in our equation. So this is our continuous growth equation for the amount of money in our account. We should get a number that's pretty similar to our other one, but it'll be a little bit more accurate as to like how banks calculate the interest. So find the value of your investment after 5 years. We're going to find A of 5. So 6,000 times E to the 0.06 times 5. Just like before, you can type this all into your calculator. Above the LN button, you should see a little E. That's the E we're looking for. But when you type this all in, you should get about $8,099.15 because it's a little bit more accurate this way, but it should be No, Richard. So when we're looking for the R here, you just turn your rate into a percent. It's different from the B. Okay. Great question. All right. So let's answer the same. Oh, this is the last example. Okay. So the same two questions will come full circle from the beginning of our lesson. When will it double? When will it triple? So when will it double? We have 12,000 equals 6,000 e to the 0.06t. And when we said that it was going to triple in value, we replaced the 12,000 with an 18,000. So that's the same as before. The different part is you have e to the 0.06t instead, okay? But our first steps are going to be the same. We're going to divide both sides by the 6,000. So we'll get 2 equals e to the 0.06t. But down here, we're going to get 3 equals e to the 0.06t. Okay. Now, at this point, we're still going to use logs to get the variable out of the exponent. So log, what's my base here? The base is e, good. Okay, so log base e of 2 equals 0.06t. And if I do the same thing down here, log base e of 3 equals 0.06t. Okay, now I think in the beginning, it's not a bad idea to write log base e. But by the time we get to the end of this course, I want us to be really comfortable writing log base e as ln. So ln of 2 equals 0.06t. And ln of 3 equals 0.06t. Okay. What's the one step I need to solve for t in both cases? Divide by that 0.06. Very good. All right, so I've got t equals ln 2 over 0.06. When you get to like calc 2, calc 1, you're just going to leave it like that, like an exact value. But I want us to practice using our calculator right now. So remember, when you type in ln, it's going to open a parentheses. It's your job to close it, or you're going to get the wrong answer. But it should give you 11.552 years. So this one, in this model, your money actually doubles a little bit faster. That's what happens when they calculate interest continuously and not like every year, okay? Now, if we do the same thing down here, we're gonna do ln 3 over 0.06. It opens up a parentheses, you have to close it. And when you do that, you should get about 18.310 years. Okay. So a more grown-up model, if you will, a more realistic model of how your money functions in a continuously compounded situation, all right? Don't be scared off by the E's and the LNs, like all the extra letters. Don't be scared off by that, okay? This is not really different than what we did at the beginning, but it is just a little bit more sophisticated and a little bit more accurate, okay? Oh yeah, where was that question? What do you mean by rounding up to the whole number? Can you maybe explain that a little bit more? You mean like when you take out a loan, it's usually for like 30 years or 10 years, it's like a whole number year. Is that what you're talking about? Yeah. So for these, we're not looking at calculating an exact payment necessarily. So we're not going to round here. We're going to keep it as like some sort of decimal form of the year. Okay. What happens when they calculate, like, here's your loan and this is how much you need to pay back every month or every year? They kind of back end it so it divides evenly into a number, but that doesn't mean that, like, if your interest rate is fixed, that it could be not a whole number year. Like, that's actually okay. But I think for payment purposes, they try and make it a whole number so that it like works out nicely for everyone. But no, we don't round up. Yeah, yeah. I see what you're saying. So, I mean, the idea here is that we're compounding continuously. So, we really want to be as accurate. Like, I would rather pay something for 11 and a half years than 12 years, right? So, we round up, what we're saying is actually going to take longer than we need it to for that particular growth to happen. Yeah. Okay. So I'm really sorry that today went super, super long. So just so we have a reminder, quiz number 1, let me type this into the chat. Quiz 1 is due by Thursday. That's tomorrow at 9:30 a.m. I have office. Val has tutoring today from 3 to 5 p.m. So if you want help on the quiz or the homework, or you just want to learn how she explains math and like sit there and kind of do your homework and ask her a question when you have one, that's totally fine too. Okay. And then I have office hours tomorrow from 8:30 to 9:30. I'm not a big fan of encouraging you to wait until the last minute, but I know the quiz is due at 9:30, so if you have any last minute questions tomorrow, stop by. I'm happy to help you out with the quiz number 1, okay? Let me take a look at quiz number 2, see what I might need to move around for that, but I will send out an announcement later on updating you on the status of quiz number 2, okay? Um, Homework number 1 is due by Sunday at midnight, so don't forget to do that. But I'll send out a reminder of like all sort of the stuff for next week on Friday, okay? So that's it for today. I'm gonna stop sharing my screen here.